Hey STEM 1 students, welcome to a short video on independent and dependent events. And we really have two learning goals for this video. You'll find them in the middle of your page. So the first one is to be able to actually identify the difference between dependent and independent events. And then also use that information to help us figure out the probability of events that are considered both independent and dependent. So if you're following along here, I'll just have you record the notes as they show up. And when we look at independent events, we're looking at really two or more events where whatever happens the first time through doesn't affect the outcome for the second event. So, um, even like picking um, picking your favorite team and what shirt you put on this morning. That those two things don't influence each other. That's a little bit different than dependent events where whatever happens in the first situation affects what happens on the second event. And those are considered dependent. And we'll look at some examples here for both of those. If I get ahead of you in the video, feel free to pause it and record the notes. So there are a few examples here for independent events, and I just wrote a couple of those down. So let's just say two completely isolated topics. You get a new car for your 16th birthday, which for some of you is a little bit away yet, but could sneak up on you here. Would be a pretty awesome birthday present. And your sister goes to college. They really have no bearing on each other. That just both of them could happen. Okay. Another example of independent events would be like the card game we played the other day where a student draws a card from the deck, puts it back, and then the next student that goes to draw has the same number of cards that they are selecting from. So it doesn't affect the total number of cards in the deck. That is slightly different than a dependent event. And so I was trying to think of, events that are coming up. So think about homecoming. And say you and your friend both want to ask the same person to homecoming. And your friend found this out and they go ask the person you want to go on the date with, they ask them first. And lucky for you, they say no. When you go to ask, that would be the second event. They could then say yes because the outcome of your friend asking can influence the outcome of you asking. So think about the other way. If they would have said yes, that obviously would have influenced the date to say no. So those are considered dependent events. Another scenario would be going back to the cards. If you draw a card, but you don't put the card back. So every time somebody, let's just say I say to you, there's 4 aces in the deck. And anybody that draws an ace gets $1 million. Well, if I go around the room and every time somebody draws an ace, we pull it out and we don't put it back in, you don't have a good a chance of winning as you did with all of those aces in there. And so these are considered dependent events because the first event influences the second. Okay, so how do we handle these when we're dealing with probability? When we have two different events, we're going to figure out each probability separately and then just multiply those two probabilities together. Okay? Sometimes there's 3 events, sometimes there's 4 events. The examples I have here all deal with 2 events, but you would just think about each event in its own conditions and then multiply their probabilities together. So let's say on the first scenario, you have these 2 cards and you pull them from a deck. You pick a queen and you put it back in the deck and then you pick an 8. So the probability of drawing a queen would be 4 out of 52. 4 queens in a deck and 52 cards in the deck. All right. And now if you notice it said we're going to put that card back in the deck. That's why on the next drawing, there are still 52 cards here. Sometimes if we don't put the card back, that'll go down to 51. So they want to know how many 8s there are, the probability of drawing an 8 after we put the queen back. There are still 4 8s out of the 52 cards. All right, if you look at those two fractions or those probabilities and multiply them, we could end up getting a pretty big number. That's why I always choose to reduce them first. If you don't, you'll still get the right answer, but you'll have to reduce the number when you get done. So I would reduce both of those to 1 over 13 and multiply across. 1 times 1 is 1. 13 times 13 is 169. So there's really only a 1 out of 169 chance that you would draw a queen and an 8 on 2 hands in a row or 2 draws in a row. Okay, let's see how that's different when we don't put the card back. So you pull it out of the stash. Well, the queen scenario, there's still going to be 4 out of 52. But what happens is if we don't put the card back, there's no longer 52 cards to pick from. We only have 51. Now, there are still 4 8s. That's why it's still 4 out of 51. But the total number of choices, since that one card is gone, is down to 51. So if we go to multiply these together, notice only the first probability reduces to 1 over 13. The second probability stays at 4 over 51. And then you just multiply straight across to get 4 out of 663. All right, these are just a couple examples. What I want you to do at this point is to complete the 4 in-class practice questions, bring them up to get feedback from a teacher, and then you can start the assignment if class time allows.